So I'm a professor in medical research at the University of Melbourne, and what I do in my everyday job in the laboratory is to try to model age-related macular degeneration using patient-owned stem cells. I'm a neuroscientist by trade, meaning that I've studied the nervous system. And the retina, the back of the eye, is part of the nervous system. So for me it was only logical to go and study the retina. AMD is a condition that is affecting many individuals, and as such I thought it was important to try and contribute to the curing of AMD. At the time when I started working on AMD, I didn't know that both my grandmothers and now my mother suffered from AMD. So I feel really grateful that I can now contribute to hopefully helping the health of people, including my own family. What we do in the lab is that we try to make new models to understand AMD. Because AMD is one of those conditions for which we don't really have good models. We've got models and they are good enough, but they're not perfect. And the problem when we don't have good model of experimentation is we can't find reason why things happen if we don't know where to look at them. And if we can't find reason why they happen, how can we find cures? So all of this means that we really need to find good models for many human conditions. There are models of AMD that people are using in various laboratories, but we thought that using stem cells we could bring a novel model to have a wider panel of experimental design to study AMD. So the model we developed is basically based on a new technology that was developed in 2007 by Professor Yamanaka in Japan, that allows us to take any cell of our body, let's say skin or blood, and turn back in time those skin cells into what we call a stem cell, which is a cell that has the ability to become everything. It can become skin or blood, but it can also become eye or brain. And so that technology has great potential for medicine because we could basically turn back any of our sample, any of our own cells into what we need to study or to reimplant in our body as we progress in some conditions. Our models are based on this technology as we are making stem cells from patients with specific conditions, and then we ask the stem cell to become the cells that are implicated in the diseases of interest. Then in those cells, which are basically grown in a plastic dish, it's like a plate in which we grow our cells and they become the cells of the eye that we're interested in, we can start looking at what goes wrong in this cell. Why does a cell coming from a patient with geographic atrophy differs from a cell from a patient who doesn't have geographic atrophy? These are the type of questions we can ask in our models. As a researcher, there are many different types of motivation. First of all, I think most of us in research, or at least in my group, we are doing our job every day because we want to contribute to a better world. And we express it through trying to contribute to new knowledge for curing diseases. That's very important to us. Another aspect we like, and I like very much in my job, is to help younger people, younger generation develop into good scientists, and see people growing, see people developing into great scientists is something I really enjoy and I take pride in doing. I would like to thank all the donors that have contributed to the funding we received from the Macular Disease Foundation Australia. To me, this work would not have happened without the support of the MDFA and of its donors. So thank you very much for your help. So thanks to the support we received from the MDFA, we were able to make a large collection of stem cells from patients with geographic atrophy, which is a late stage form of AMD. And we made 60 patient stem cell lines out of patients with GA, and we compared those cells with cells from control individuals who did not have eye disease. Once we made the stem cells, it's one thing to make stem cells, but we're not really interested in stem cells. We want to understand what goes wrong in the eye. So we basically guided the stem cells to become the retinal cells that are affected in AMD and in geographic atrophy. And then by comparing the two cohorts of geographic atrophy cells versus the control cells, we could start identifying the differences between the two cohorts and what might be going differently in the cells from patients with geographic atrophy. And our results show that the mitochondria, which is basically the energy factory of every cell, was working differently in the cells of the retina, or the retinal cells, I should say, from patients with geographic atrophy. So it implies that the energy production and perhaps the energy consumption is different in the retina of people with geographic atrophy.